Okay, today I'm going to cover chapter 18. I know that doesn't mean much to you, but just talking about the stellar graveyard, specifically focusing on white dwarfs, neutron stars, black holes, and then talk a little bit about gamma ray bursts. So remember, white dwarfs, okay, there are the remaining cores of dead stars. So they're down here in the HR diagram. And what supports them is this pressure on the inside called electron degeneracy pressure. And it overcomes the gravity, so gravity doesn't collapse upon it. White dwarfs cool off, they glow dimmer as time moves on. So this next slide talks a little bit more about electron degeneracy pressure, where electrons have basically run out of room. Remember, electrons orbit the nucleus of an atom, and they have like certain spins, only 2 electrons in a certain orbital. We talked a little bit about this in Gen Chem, but the electrons prevent further collapse. However, protons and neutrons are still able to move around. Whereas with neutron stars, which we'll talk about, electrons and protons combine to form neutrons, and the neutrons run out of room, and they prevent further collapse. And that's why neutron stars are really, 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 really small, like only the size of a city. And then we'll talk about black holes, where gravity overcomes. There's no internal pressure on the inside. There's no electrons, no electron degeneracy pressure, no neutron pressure on the inside. So nothing prevents the collapse. The collapse occurs, and now you end up with a black hole. So the size of a white dwarf has about the same mass as the sun, but it's about the same size as Earth. Okay, so it's the mass of the sun squeezed into the shape of Earth. High mass white dwarfs are smaller. So as you increase in mass, the white dwarf gets smaller in size. There is a limit to a white dwarf, and that's about 1.4 masses of the sun, where electrons have to move nearly at the speed of light, and we know that nothing moves faster than the speed of light, so nothing can really be more massive than 1.4 mass of the sun. So we call this the white dwarf limit, or the Chandrasekhar limit. Now, sometimes white dwarfs can be found in binary systems. Okay, so a star that started with less mass gains mass from its companion star, and then eventually the mass-losing star will become a white dwarf. And then what happens next? Well, you might end up with something called an accretion disk, where mass gains angular momentum and it starts to spin and flatten into a disk called an accretion disk. We have friction going on in this process, and then angular momentum as well, and the disk can heat up and start to glow. Okay, novas. So here's our white dwarf, here's that companion star, and it's gaining mass, as you can see here. So the temperature of the accreted matter becomes hot enough for hydrogen fusion to take place, and then when fusion occurs, it occurs very suddenly, very explosively, resulting in a nova. And obviously, a nova star system temporarily is brighter, okay? And the explosion can drive out this matter that's been floating around here into space. Now, there are 2 types of supernova or novas: massive star supernovas and white dwarf supernovas. And so massive stars, total explosion. You end up undergoing an iron core starts to form. So, you know, hydrogen forms helium, and helium starts to form some heavier elements in the periodic table. And once you start to get to iron, then you're getting pretty close to a supernova. So it reaches its white dwarf limit, it collapses upon itself in this total explosion. White dwarf supernovas, you get carbon. So not quite as heavy as iron, but, you know, still kind of heavy. And it reaches the white dwarf limit, causing a total explosion as well, but it's just not as great as a massive star supernova. And so there's one way to tell the difference between the two, and that's just to look at the light curve. So in red here, we have our white dwarf supernova, and then over here is our massive star supernova. And it just shows how luminosity changes over time. So nova or supernova, a supernova is much, 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 much more luminous. Okay, novas, you get the hydrogen to helium fusion in that accreted matter, and the white dwarf's left intact. However, when a supernova occurs, it's a total explosion of that white dwarf, and nothing is left behind. And so I just said we looked at light curves to tell the difference between the two. But then we can also look at how their spectras differ, whereas with exploding white dwarfs, you don't really get that hydrogen absorption line. So neutron stars, so that was white dwarfs. Now we're moving on to neutron stars. What are they? It's left behind after a massive supernova. Okay, so our degeneracy pressure of neutrons supports against gravity. The electron degeneracy pressure goes away, so now we have protons and electrons combining to make neutrons and neutrinos. And when these neutrons collapse to the center, that's why we call it a neutron star. And neutron stars are very high, they're highly compacted, but they're shoved into a very, very small area, the size of a small city. Like a teaspoon of this stuff is extremely heavy. I should have looked up the fun fact that about a teaspoon of a neutron star, if you were able to scoop it out, it's extremely heavy. So how were neutron stars discovered? Jocelyn Bell, back in 1967, using a radio telescope, discovered pulses of radio emission coming from a single part of the sky. And these pulses were coming from a spinning neutron star. And so a spinning neutron star is sometimes called a pulsar. And so the Crab Nebula has pulses 30 times per second. Pulsars, okay, so here's our neutron star, and there's this beamed radiation being emitted out, and the neutron star is spinning, and as it spins, these pulsars kind of act like a lighthouse, like a beam of light rotating around, very similar here. So pulsars are kind of like lighthouses, if you will, where beams of radiation along a magnetic axis are not aligned with the rotational, but as it spins, sometimes we can measure that, just like Jocelyn Bell did with a radio telescope. Okay, so in a close binary system, where there's two stars and a neutron star, one of them's a neutron star, matter can fall into it, forming an accretion disk, just like with the white dwarf binary. It adds to the angular momentum to the neutron star, increasing its spin. And as it becomes hot enough for helium fusion, X-rays can burst out from this process. Okay, moving on to black holes. Now, a black hole is an object where gravity is so great that not even light can escape it, hence the name black hole. The surface of it is the radius at which the escape velocity equals the speed of light. So in order for an object to escape like a planet, it has to overcome like gravitational forces. So we call this the escape velocity. The spherical surface that you see here down here is called the event horizon. I believe Netflix has a movie called Event Horizon, and it's probably got to do with black holes. But the radius of this event horizon is called the Schwarzschild radius. And I was going to read something here about, I think it's maybe on the next slide, yep. So the event horizon of a 3-mass sun, so 3 times the mass of our sun, black hole, is also about as big as a small city. Earth would have to be less than a centimeter for light to not be able to escape from it. As you increase in mass, the event horizon is larger for black holes. And then the black hole's mass strongly warps space and time in the vicinity of its event horizon. So I'm going to talk a little bit about these diagrams here. This is a 2-dimensional representation of flat space-time. And you can see that we each have these pairs of circles separated by the same radial distance on the way out. Now, a mass does affect this sheet similarly to the way gravity curves space-time. So if you imagine this as a sheet here and we have a ball, we get this nice like curvature going on as we move closer to the mass. So as you move closer to the, oh my gosh, my mouse is frozen. As you move closer to the mass, the space-time starts to curve towards it. So the curvature of space-time becomes greater and greater as we approach a black hole, as you get closer to it. And the black hole itself is just a bottomless pit in space-time. So, yeah. So nothing can escape within the event horizon because nothing can go faster than the speed of light that we know of, although I've heard neutrinos can, but yeah. No escape means there's no more contact with something that falls in it. It increases the whole mass, it changes the spin or charge, but otherwise it basically loses its identity as it moves through that event horizon. Okay. There is a neutron star limit. So neutrons in the same place cannot be in the same state, just like with electrons. So we have our neutron degeneracy pressure that is trying to press against gravity, but when it can no longer support, then gravity overcomes it, and they figured out that 3 masses of the sun is where gravity overcomes it. So some some massive star supernovae can make a black hole if enough mass does fall into its core. Okay, this final thing about singularity. Hold on here, I'm just going to see if I can find it in this book because I saw it earlier. Oh, no, now I lost it. Shoot. Okay, anyways, oh, here it is. All right, so singularity. By definition, gravity crushes all matter into a single point. We call this singularity. It goes beyond the neutron star limit. No known force can resist the crush of that gravity. So it says right here, because nothing can stop the crush of gravity in a black hole, we expect that all the matter that forms a black hole must ultimately be crushed into an infinitely tiny and dense point in the black hole's center. We call this point a singularity. In a rapidly rotating black hole, the singularity may stretch into the shape of a ring around the center rather than being a precise point. Unfortunately, this idea of a singularity pushes up against the limits of scientific knowledge today. The problem is that 2 very successful theories make very different predictions about the nature of singularity. Einstein's theory of general relativity, which seems to explain successfully how gravity works throughout the universe, predicts that space-time should grow infinitely curved as it enters the point-like singularity. Quantum physics, which successfully explains the nature of atoms and the spectra of light, predicts that spacetime should fluctuate chaotically near the singularity. These are clearly different claims, and no overarching theory can reconcile them has yet been found. So we don't fully understand how a singularity behaves until we develop a new theory that encompasses both general relativity as well as the quantum mechanics theory. So, yeah. So what would it be like to visit a black hole? Well, if our sun became a black hole, gravity would be very different, only near the event horizon. In other words, a lot of times we think of black holes as like giant vacuums that suck things in. That's not the case. So light waves take extra time to climb out of the deep hole in space-time, leading to a gravitational redshift, very similar to our Doppler shifts. So we can kind of measure that change. And also time passes more slowly near the event horizon. So if we, notice that the event horizon as a hollow point here, I'll go back right here, okay, down here. Time moves more slowly than it does out here. And then there's this scene in Interstellar where they visit a planet that's close to the event horizon of a black hole. And they leave one team member on the spaceship, and 2 people go down to the surface to investigate where a scientist was sent earlier, years prior. And time moves more slowly on that planet. And then when they return, they see that their teammate, their crew member, has aged significantly due to this phenomena. So, yeah. Tidal forces near the event horizon would be lethal to humans. You'd get squeezed and stretch. It would be gentler near a supermassive black hole because its radius is obviously a lot larger. So do black holes really exist? Well, we do have some verification process. We need to measure the mass by using orbital properties of a companion star if possible, measuring the velocity and distance of the orbiting gases around it. If it's a black hole, and if it's not a star, its mass exceeds the neutron star limit, which is approximately 3 masses, or 3 of our solids. Okay, the final section I want to discuss is the origin of this process called gamma ray bursts and what causes them. So in the early 1960s, the United States began launching a series of top secret satellites to look for gamma rays emitted by nuclear bomb tests. And pretty soon these satellites began to detect occasional bursts of gamma rays, lasting for just a few seconds. And it took them several years for the military scientists to realize that these gamma ray bursts were actually coming from space and not from some, evil human activity from the enemy. So they publicized their discovery, I think, in the 70s. And at first, astronomers assumed that these gamma ray bursts were just a variation of X-ray bursts that could occur on neutron stars. But the truth turns out that it's a little bit cooler. According to recent observations, these gamma ray bursts seem to come from the formation of black holes at very great distances from Earth. So it's actually kind of cool. And although the process that produces gamma rays is still unknown, it's still unknown. So observations show that at least some gamma ray bursts are produced by supernova explosions, and others form from collisions between neutron stars. So kind of cool. Okay.